Yeah, Dr. Shiva?
Yeah. Hi, Professor. Yeah. Yeah, hi everyone. Welcome you back again to the lecture 12 on the structured CAN codes. Lecture will be on protection microgrids by Professor Saad McKelvey. Handing out to Professor Saad McKelvey to deliver the lecture. Professor, you can take. Professor, you are not audible. Professor Saad? Thank you.
Yep. I think, is it all good?
Yeah, it's all good.
Okay, thank you very much. I think there is one, just now, before we break, there is one question on the master. Okay, just a minute. Master slave control belong in which hierarchy? Let me go back. Sorry, I missed that. No. Okay. Okay. If we look into this the hierarchy, the control, which the question was, the master slave control belongs to which hierarchy? So it belongs to the secondary control, okay, because it's in charge of voltage and frequency regulation, right? So that's the question. I don't know if the person is able to hear us. So that's the answer for the questions. Okay. Now I think we have discussed the all control, peer-to-peer, master slave, and then we are now in I think the last part of the control, which is the control methods that's been used. And as we explained before, okay, so the main objective of operating this control is to make reliable operations in both grid connected and also islanded mode. These are the two modes of operations. And depending on the DG operating conditions, there are three main types of control method that usually we use. PQ control, VF control, and drop control. Okay, so we will be reviewing each one of them. For example, if we talking about the PQ control, okay, so the main objective of this is to control active and reactive power constant when the frequency and the voltage deviations within the limit. So the main objective of this is always to maintain the active and reactive constant, okay? And maybe move to the next slide, maybe better. So the PQ control, like I mentioned just now, is to keep the microsource active and reactive power always constant when the frequency and the voltage deviations is within the limits, because the frequency and the voltage, you always have a limit, for example 50 plus 0.5 to 49.5, within that range. In the PQ control also, the active and reactive power are firstly decoupled in order to achieve independent control. Okay, so we control independently PQ and they decouple first, and then The reactive power controllers aims to maintain the active power output constant at a given reference within the range of frequency, and the controller for the active power is to maintain the reactive power within perceptible range of voltage. So these are the two main constraints. So frequency always related to the active power, voltage always relative to the reactive power. So they are decoupled, okay, and then it's been measured, and then this is in case in what you call grid connected mode, okay. However, in islanded mode, PQ and control method cannot be maintained, okay, cannot maintain the frequency and the voltage. So there should be an extra distributed generator is needed to regulate the voltage and frequency, and that's what we said just now before the break. For islanded mode, there should be another source that is responsible for regulating the voltage and frequency, okay. Yeah, if it's operated in grid connected mode, I think that's the grid is one responsible of maintaining the voltage and the frequency for the microgrid. So this is the what we call how the PQ control works actually in microgrid systems, either in grid connected mode or in what we call islanded mode. For the second one, which is the VF control, okay. In the VF control, the objective of the VF control is always to maintain the system frequency and voltage magnitude constants, regardless the actual active and reactive power outputs of the DG. All right. So frequency control adjusts the active power, okay, and the voltage control adjusts the reactive power output to maintain the voltage within given values or given reference. So the VF control is common when the microgrid operates in islanded mode, mainly commonly used in islanded operations. Okay, so these are the summary actually of these two. We can go in the detailed loop of these controllers. Okay, the last control method or the control type that can be used is what we call the droop control. Okay, the droop control, it's a very commonly used and widely used, and has been used for many years so far, and also reported in the literature. You know, many papers has been published on this. Different methods has been to be used. Okay. And it's the drop control. It's one of the key solutions actually for sharing the demand power between generators, okay, in autonomous microgrids, okay, where there is no support from the electricity distribution system. So this is when we share, you know, from power sharing and demand power from different microgrids or different DGs. Okay, so under the drop control, we have what we call the active power control. Okay, the active power control, you know, and in this drop control, the first one is to keep the load keeps changing. You know, as we know, the load is changing all the time, so the generators will change their power output based on the frequency deviation. So this is the key what we call equations, or the key formula of the drop control. So the load, when the load changes, automatically will lead to their power output based on the frequency deviation. So, and it can be described by this formula, or maybe from this graph, which is much easier. So here we have the power, okay, and here we have the frequency. Okay. So for example, when there is a power change, okay, there is a power change here, okay, so what that leads, okay, and or there is the frequency change. So, and this can be actually formulated in this formula, which is delta P, P2 minus P1 equal to SP, which is the slope of the curve, this here, times F1 minus F2. So this is the formula that actually we use always in the drop control for this is active power and frequency. And the same goes to, maybe before going to this one, the same goes for the voltage control. Okay, for the voltage control is also the same. So when the linear relationship between reactive power and the voltage, so whenever there is a change in what I call in reactive power or the voltage, so that leads to so for example, let's take this point here. For example, this is Q2 here. Okay, so yeah, maybe we can put this is Q1 and this is Q2 here. So Q2 minus Q1 times the slope V1 minus V2. Okay, so this is the basic formula for the what you call for the drop control. So there are two main formulas. One is related to the active power, okay, change with to the frequency. Another one is related to the active reactive power and the voltage. So if we look into the block diagram, you know how this drop control is being implemented or can be implemented, or I call it conventional, you know, because there are many modified and improved control techniques. So what you can see here, so we have a different DGs, okay, and these different DGs, so we measure the voltage and the frequency, and then we have the PQ calculations, okay, and then here would be P2 minus P1 and times M, which is the slope just now we define. The same thing here, Q times Q1 minus Q2, Q2 minus Q1 times the constant here, or the slope, and then we have the reference, what you call voltage, and then we have here the reference frequency, okay, and we generate what would be the voltage and what will be the frequency, and that actually gives the voltage reference to the voltage and current loops, and then we'll generate the PWM, and then it will control the inverter or things. And you can see here we have the PWM pass width modulation control, which connected to the gate drives of the inverters, and then it will. So this is how it works with drop control. It's quite actually very simple and very straightforward. You know, it's based on the voltage and current and the change in voltage and change in load, and then that will result in doing this. So that's actually the conventional, or yeah, it's actually even the modified one are similar to this. Okay, so this is about the three what do you call the three control methods that we usually use. Okay, and as I said, these are typically used either in a grid connected mode or in islanded mode. Okay, all right. So the second part of the discussion actually will be on the need for protection of microgrid. You know, what do we need? You know, in the protection. You know, so because the grid, the microgrid can be operated in two modes. So there in grid connected mode, the fault current of a higher magnitude. You know, so because it's a grid, you know, the fault current can be very high. You know, so. And that's actually one of the questions yesterday or the day before yesterday on the grid fault. You know, so one is grid connected. So unfortunately, we need to consider the grid fault. It's quite high. So it will be like 10 to 50 times the load current. Okay, from DTT in order for the active conventional or protection device. So on contrary, in standalone mode, okay, the microgrid fault current is about 5 times of the full load current, you know. So we're talking about 10 times or more ratio, in 2 modes. And that's actually make it a bit challenging. So to what level we are going to size these protection devices. Okay, so to avoid communication failure, okay, adaptive protection schemes or alternate means are needed, okay, to cope up with those issues. So protection system design for microgrid pose significant challenge due to the bidirectional issues. So we have bidirectional power flow, okay, from the DG, as well as what you call lower current levels due to the inverter connected to the grid. So these are some of the challenges that we face in the protection of the microgrid. First one, as I mentioned before, the short circuit current level. It's quite significant, especially in the grid connected mode. Okay, false tripping. Okay, so sometimes we face this I call case where we have false tripping. We will discuss all of this. What does means each one of them. Then blindness of protection, and then automatic reclosioning and synchronized reclosioning, because when you have the disconnect from the grid and then you want to reconnect, that actually causes what you call problems. Reach of independence relays, bidirectional. Yeah, this is an issue, which is bidirectional power flow, and some systematic tripping, single phase power, okay, insertion. So let's look into the first one, which is the short circuit current. Okay, so if we look into this diagram, you can see here what you can see. We have the DG current, and then we have the grid current, and then it's a total current, which is, for example, the fault here happens. So in AC, this is an AC microgrid. The short faults are approximately 10 times or more than the rated current due to the large fault current. Okay. However, in DC grid DC microgrid systems, the fault current are restricted by the converter because it's a DC. So they are normally less than the threshold values. Okay, so the issue for this short circuit current, especially in grid AC microgrids and with the grid connected. In the islanded mode, the fault current is 5 times greater only. So that, like we mentioned before, than the threshold, as the DR only contribute to it, because here in islanded mode, so there's no grid here. So the only thing is the DG, what I call contribution. Okay, so as a result, okay, the fault level in the grid connected modes operation is larger. Okay, so I think that's what we mentioned just now. The other issue is on microgrids protection is the false tripping of the feeders. Okay, may occur, for example, due to the failure of PCC, the point of common coupling. Okay, device. Okay, so whether the fault is on the utility side or on the microgrid side. So this may result in increased cost due to more operation of the PCC, okay, and decreasing its lifetime, because and increasing maintenance costs. That will be so. Moreover, fault trips can result in microgrid exposure to power quality problems. Okay, so this is one of the issues. That's sometimes we have a false tripping due to different reasons, different part of the circuit, and may lead to loss of revenues. So, and the other one, which is the blinding, of protection. Okay, so maybe I think someone need to mute, if possible, please, because there is echo. Okay, so blinding of protection. Okay, where if you look into here, we have transformers, we have the relays, and then we have the distributed generators, and the fault happens here. So the feeder here in impedance determines the the pickup current, okay, and greater than the feeder rated current. So this is another, and this is called the relay operating zone with respect to the feeder impedance changes is known as called the blindness protection. Also, sometimes we call the not allowed due to the transients, the reclosure operations of particular radial distribution systems, clear transient faults, So sometimes we may have a fault, which actually it's not really a fault, but that leads to the DG still to provide the fault current, and this is it's referred as prohibition or automatic reclosing of the contact. The unsynchronized reclosures. Okay, so this is another issue when we want to reconnect to the grid. Okay, when we want to reconnect to the grid, okay, the closure, it's not done synchronizing, and due to this connection without considering synchronizations, then it will lead to this kind of faults, because maybe the microgrid was operating on isolated or non-connected, not connected to the grid, and then reconnect back to the grid. And during that reconnections, it's not done, it's not synchronized, and that actually can lead to these issues. Okay, I think one of the also major issue or major problems is the bidirectional power flow. Okay, so bidirectional power flow is in the feeder of microgrid is one of the major challenge in case of DG, integrated, So there is a possibility of power flows in reverse direction. Means supposed to go from this DG to the grid, and then it flows from the grid to the DG. Okay, and this may may lead to many issues. Either from the DG to the grid. When the local generation level surpasses the local consumption level, so means the grid, the DG keep pumping the power to the grid, and and it is saturated, saturated. So that's actually one of the issues of these bidirectional converters. But I think this has been recently addressed. Has been addressed recently, and especially with smart inverters and smart converters, and sometimes we may use different devices for protection from this kind of issue. Sympathetic tripping also, that's when we're having a system, okay, tripping occurs when the protective device activate in external protective zone, outside of the zone of the protection. So it's in proper protections. So that's actually also another issue which can be faced. So these are all the challenges we have seen. It's related to EC microgrids, So we have quite a number of challenges, but as I said, most of them have been already dealt with. For example, the short circuit current level. So we have devices which can handle high. We have problems now for stripping. This is also been addressed. Bidirectional power conversions control techniques has also been addressed. So there are quite a number of solutions actually addressed in microgrid operations. So how about the DC microgrid? Okay. In the DC microgrids, there are other challenges. Okay, some of them may be similar or related, like for example the short circuit current. Okay, so one of the issues is the grounding. Why the problem is the grounding? Because the grounding is we have a distributed generators. Each one have its own grounding. Okay, so this is one issue. So we have different sources, PV, we have wind, we have different groundings. So this is one of the issue. Fault current direction, okay, because here it's a DC. So that actually makes a lot of difference compared to AC. So we have a non-zero crossing because it's a DC, so the detection becoming a challenge. So we don't have a zero crossing here. Okay. Also, there is a high sensitivity of inverters to fault current. Okay, so this is also an issue where inverters, usually are very sensitive to fault currents. Means they can trip anytime. So small current increases or above certain limits, then they trip, and that may result in frequent tripping. So, but this can be adjusted. We can adjust actually what will be the limits of the fault current. Also, sometimes it's the wrong use of AC breakers in DC microgrids. Okay, so this is an issue. So that's actually that's why I think I mentioned before that for DC systems we need to use DC cables. We need to use DC fuse. We need to use DC circuit breakers, DC switches, DC connectors, everything. So, but mixing sometimes, this using not the right device can lead to this kind of. And then I think we have explained the change in short circuit current and difficult to coordinate between over current release. So that's actually one of the issues that we face in when we're having in DC microgrids. Okay, this is the tool for. Let's look into what I call the dynamic faults current magnitude. So, like we said, it's an issue because sometimes it goes 5 times, sometimes it goes 10 times, it goes up to 50 times. And there are different fault types. It's either line to line or line to ground, okay? It can, the fixed setting of this relays, which is for particular fault conditions, create maloperations. Sometimes if you set it too low or too high, okay? So that can lead to what I call setting this overcurrent relays, and the overcurrent in the DC microgrid suffers from the dynamic fault current due to the interlinking with the AC utility. So this is because we have two systems connected to each other. One is AC, another one is DC. Okay, so under fault situations, so this is AC grid effectively changes the short circuit level. So this is one of the challenges actually that's being faced when we're having two systems are connected to each other. Okay, the remote operation of DC microgrids in autonomous mode has a different fault level, same like AC microgrid. So when it is operated on a autonomous or islanded mode, it has different fault levels. When it is in a grid mode connection, it has different fault levels. Okay, so the converters are, primarily entrust, okay, the fault current, to their safety. So always try to, means setting in terms of protection of all the switches and all the control boards that is connected to the inverters. So in terms of bidirectional faults current, DC microgrids are interfaced, or connected to the AC through a bidirectional converter. So this is the issue here, because when you have a DC microgrid and then we have an AC grid, so in between there is a bidirectional converter that allows the both directional to flow. So the location of the DG is also exhibit the fault current from both directions, from DC and AC. So the changes is also promote bidirectional faults, which is, we undermine the non-directional relay operation. So that's actually one of the issues. To enhance this, so the direction features must be incorporated into the protection of the design, or so this is all related to the bidirectional converter that actually fault can go from AC to DC, from DC to AC to the AC side. Okay. So in terms of the dynamic current due to constant power load, okay, so the load and the converters installed at the load end with the closed loop control, behave as a constant power load, or we call it the CPL. Okay, so under the fault condition, voltage decreases very fast. Okay, constant power loads draw massive current, to maintain the power constants, which accelerate the fault currents. So under a standalone mode of operation of DC microgrid, constant power loads elevate the voltage and current oscillations. Okay, so try to maintain, try to withdraw constant power, for as much as possible. Okay, and then the last one, it's the effects of grounding. Okay, so I thought not the last, I think before the last, So effects of grounding configurations decisively influence the faults, like I said before, especially for DC microgrids. So the fault current magnitude is profoundly affected the grounding. So proper configuration of grounding is very essential, especially in designing DC protection systems. All right, so this is grounding. I think there's also for this also there is some standards that we have to follow, especially for grounding and how it has to be done in DC microgrids. I think we also mentioned before on the zero crossing. Okay, so in absence of neutral zero crossing, so DC, fault current is big obstacle, as it does not contain natural zero crossing. Okay, so fuses can be implemented to chop the fault current for a low impedance. So this is one of the major issues. So the transient over voltage is also the hindrance to fuse operation. Okay, so this is another issues. Also, in the DC microgrids, there is less virtual inertia, and because all of them are DC. Okay, so this DC interleaved microgrid suffer from virtual power instability and oscillations due to the AC side disturbance, which causes some momentary faults on the DC side. Okay, so what to do to protect this? This is how to do the protections. Okay, so DC protections is mainly two types. Okay, unit and non-unit type protections. Okay, for the unit protections scheme, okay, specifically implemented to protect from fixed zone of the DC microgrid and used to protect the DC bus, converters, energy storage systems, devices, loads, and so on. Okay, so the current differential protection is also most commonly implemented in unit protection. Okay, so also the non-unit protection, okay, it relies on the predefined threshold setting of the electrical quantities operation. So non-unit protection includes the overcurrent, under or over voltage, current and voltage deviations, and so on and so forth. So these are the two ways and schemes. And there are a few strategies, actually. There are a few strategies that we use in microgrid protection. So one is adaptive, so protection strategies to try to adapt to the fault. The second one is differential, okay, and for example, like if we look into the adaptive approach, the ability to the power system to adjust itself with the current operating condition. So try to, adapt to itself, without external, what we call interference. Okay, by adaptively changing, okay, the related setting according to the operation condition. So it's adaptive, from the word adapt, to the current conditions. The other one is the differential protection. For differential protection, okay, scheme follow the fundamental of the KCL, the Kirchhoff's current law, to operate at the time when the difference of the current entering and leaving across the feeder exceeds the predefined threshold. Okay, so this is the basic principle. So it's independent. It has an independent effect, okay, of the short circuit level. So DG integration, DI over DT parameters variations, and also quite important. The other strategy, which is we call it distance protection. Okay, in the distance protections, the fundamental principle of this protection method is used in AC microgrid, and is based on the distance measurement through calculating the short circuit impedance between the fault and the protective device. Okay, and most of the time this is preferred in transmission lines. We want to know the location of the faults. So this is usually for it's heavily used in, like I said just now, in transmission lines. Also, we have another method, which is single processing or based protection strategy. Okay, so in this we use wavelet, okay, transformers based protection, okay, or the transformers, the S transformers based protections, or what you call these different methods actually, schemes that can be used. Okay, and then I think the last intelligence, before the last one, intelligent techniques, also protections. So this is using AI or advanced techniques, so applied in designing the protection scheme, for the power system due to error. They are quite successful, and they are quite actually good in terms of providing fast response and reducing the error. And also, one thing about this AI is they're able to adaptive learning. So they will learn from previous scenarios, and also they can make a decision faster. And that's actually what we require, especially in the microgrid systems or in power systems, is the response time, and also the reduction of error and adaptivity. Adaptivity is a key issue here. Okay, ENN is one of the most prominent techniques that is being used in fault classifications and detection. Okay, because there are two things here. One is the classification of the fault, okay, and then the detection. So because you can detect the fault and then you classify it later, that's also possible. So, but this is very important. So to know the techniques that is being used. Also, we have the last one. I think this is the overcurrent based protection. Okay, so in overcurrent propagation, we used to protect distribution lines of electrical grid integrated to the DAR. Okay, so the relays are used. Okay, such as schemes could be directional, operating in front of event, or non-directional. Okay, and these are some of the devices actually that used for protections. Either it's in a AC microgrid or it's in a DC microgrid. So there are fuses, switches, circuit breakers, sprinklers, and then, for example, in AC microgrids, we have fault current limiters and other devices that can be used into this. So there are other points which I would like to mention before. Maybe if we have some time, we can go to the energy management part. I'm not sure if we have some time, and maybe if we have any questions here before we move to because maybe I have another 15 minutes, but I need to move to any questions or any before we move to the next. Maybe I will have another 15 minutes.
Any questions from the participants?
Because we need a bit to be faster. No, this one. 7, 8. 7 by 8. Yeah. I think maybe spend another 5-10 minutes, 10 minutes, and then we maybe leave 5 minutes for questions, even for the previous session and the current session. So, yeah, just a minute. I would like to share this before we end. Yeah, this one here, screen number 1, share, and PowerPoint, lecture 8, screen sharing, and then setting. View. Yeah, just a brief what I call on the energy management, because also this is it's very important. It's related more or less to the control, but sometimes we may lead differently. So first one, we will define why the need of energy for microgrid energy management systems. You can see here centralized and decentralized. This is related to the control which we have seen before, and different techniques that's used in the what I call energy management system. So what is the definition of this energy management? So the International Electromechanical Commissions in standard IEC 61970, okay, which relate to energy management systems applied application program. Okay, so it's defined as a computer system or comprised software platforms providing basic support services and a set of applications providing the functionality needed for effective operation of electrical generations and transmissions facilities, so that assures adequate security and energy supply at minimum cost. So this is actually definitions of the energy management, and this is energy management does not it exists in even in the large grids. How you manage your okay. So why the need for this energy management system? So most of the time, microgrids have a limitation. Okay, especially due to the high cost investment in renewable energy storage systems. Also, sometimes it's the high deployment, in intermittent of renewables. Okay, and then energy management systems of microgrid, so it's maintain both, the supply and the demand side management. So we have demand side management, and then also the we call the supply side management, while satisfying the constraint. Okay, so so energy management provide the many benefits from generation dispatch to energy saving, reactive power support, frequency regulations, which we have covered actually in the control part. As I said, there is an overlap. Okay, a lot of overlap between the control. So these are some of the needs why why do. So we always, when we design the microgrid systems, we have a set of objectives, and then also we have a set of constraints. Okay, that's we want to fulfill. Okay, so for most of the time, for example, we concerned about the operation and the cost of the storage system. We want it to be as small as possible. Levelized cost of renewable energy resources, operational and maintenance of cost of what we call the grids, energy transition, battery degradations, outage interruption costs, demand response time, what we call incentive, sorry, demand response incentive, losses, costs, load shedding, and the greenhouse emissions. So we have a multiple objectives, So and also we operate within constraints. I think some of them we already explained, which is, for example, reactive power support. What they call there are some physical limits, okay, for energy storage systems, for energy balancing. So there are big objectives, but we have also set of constraints that we operate. Okay, so in microgrid energy management systems performs variety of functions. Okay, not only you call just now we talk about frequency and oh sorry. Can you okay? So for example, monitoring, okay, analyzing, forecasting, power generation of the AR, load consumption, energy market price, and meteorological factors. So we can see actually it performs a lot of more than what the control within the microgrid do. Okay, so we have like renewable energy sources, we have storage, we have DR, we have EVs, we have grid, we have weather forecast, and this data, okay, and then we do the data analysis and then forecasting, optimization based on the energy market, and then real-time control, and so on and so forth. So this is what we call energy management. Energy management is not only controlling the frequency and the voltage, but taking external factors that affect the performance or how this control will be performed or be implemented. So that's just want you to understand the difference between the control of microgrids and the energy management of microgrids.
Okay, sir? Just
yes, sir.
Yeah, sir. The screen has not yet shared.
Really?
Yeah, it was somewhat problem.
How about now?
It is not yet.
Not yet, sir.
How about now?
Please go back again to share, sir.
Is this happens after I switch or
maybe after you switch?
Oh, sorry, because I switched to a new. So you didn't see any share. Entire screen one. Okay, and then where is my PowerPoint? I don't know. Are you seeing?
Sir, you can share it, sir, again.
Yeah, okay. Share entire screen number one, share, and then put the PowerPoint, and then put it on the slideshow, and then display setting, view.
Yeah, it is fine. It is fine.
So have you seen this one before?
Yeah, we have seen this one.
Okay, good. So that's actually the main difference, because we want to show you the difference between the control of microgrid, which is what you have seen before, and the energy management in microgrid. So energy management is more, what you call, okay. So I'm not going to go into these details. So I think we have discussed decentralized, centralized versus decentralized. I think we have done this. So the different types of energy management used in microgrid. So there are quite a number of them. So energy management based on classical techniques used, based on meta heuristics like PSO, all these techniques, approaches, based on artificial intelligence techniques like the AI, ANN, and other techniques, based on stochastic and robust programming approaches, based on predictive control. Also, this is also another area where predictive just a minute. Predictive control techniques, means based on history, can do the prediction. So there are actually quite a number of them. So, for example, maybe looking to some classical energy divide into two. Okay, so mixed integral programming, or so these are some different methods. Unfortunately, we don't have much time, but so these are some meta-heuristic techniques which we use, and this is actually, like I mentioned before, these are some of the areas of research which PhD students can work or whatever, But so, for example, genetic allopatric PSO, DE, ant colony, so many fireflies, and these are all reported in the literature, and this is the applications, the methods, and how they've been applied or being used, in different applications. Also, artificial intelligence, starting with the classical artificial intelligence, which is the fuzzy and neuro, multi-agent, game theory, and so on, adaptive intelligence techniques. So this is the comparison and the applications where we use them, for example, So, for example, here the game theory, the objective are to achieve maximum utilizations on the presumed level and maximum profits on the microgrid. Okay, so different techniques they perform better in it. So also programming approach, we have also quite a number of methods that can be used, and this is the comparison. Anyway, I will share this maybe if some of you are interested. And also the references, you can, this is based on the predictive control, as I said before. Predictive means you're predicting what's coming, based on the history, based on the previous challenges. Okay, and I think maybe we need to stop and give at least, because another 3 minutes only left. So maybe we can stop, maybe give some time for questions or comments. Unfortunately, the time, constraint, especially today, means I was thinking it is 3 hours, but it turned up only 2 hours, and it's so maybe we can open we have another 3 minutes. Any questions, or maybe stop presenting? We see the chat.
This energy management control is a offline study, is it?
Sorry?
The energy management control, is it offline study only, right?
Yes, it's offline. Yep.
Okay. Yep. Where you should have a thorough knowledge of the entire microgrid.
So it's based on data that you collect. Okay, yeah, it's based on the data that you collect. It's offline and design and then deploy. Yeah, because it does not use only the actual system, data now, but it uses historical data. For example, wind speed, using solar irradiance, using load profile, using. So it's a combination of a lot of data which cannot be provided. Online. Yeah. It's offline.
Okay.
Yep. Okay. Any other questions, or guys? All right. Still have some few minutes. So, in a standalone DC microgrid, suggest some control strategies required to be implemented. in standalone DC microgrid? I think some of the control techniques which we have seen, okay, can be applied in DC microgrid. DC microgrid is relatively easier to control if you have a full DC microgrid. Okay, when I see here your question is on standalone, means it's not grid connected, because if we have a grid connected, that's different issues. Actually, we have more challenges. But if it is a pure DC microgrid, okay, there are many control. You can use the predictive control. You can use different controls that need to be implemented and used. Even simple control techniques also can be used. DC, usually when we deal with DC isolated standalone, it's much more simpler actually to work. Any simple control technique can work. Okay, any simple control technique. Okay, good. All right. Okay. In an installed 5 kilowatt grid connected PV in an organization, what the analysis further can be carried out for research? In an installed 5 grid connected PV systems in an organization, what analysis? Yeah, if you have a grid connected systems, so what are, if I understand the question correctly, what research can be carried out, for research, right? I think so. That Dr. Siva, is that the question, right?
Yeah.
Yeah, it means what? So if you have a grid connected PV system, 5 kilowatt, I think we have few research can be done, especially if you have a weather station. So you have the data, means you collect the radiance and you collect the temperature and the wind. So you can do forecasting for this 5 kilowatt grid connected. So you have the power also that injected to the grid, and then you can test your system actually. Does it predict the amount of power generated or not? So this is one which can be as easily done. The second one is you can study the degradation, how your system degrades. For example, after a few years, okay, few years, what happened? Okay, after a few years, what happened? Means the degradation, in terms of efficiency of the grid connected PV system. So study the degradations. For example, this year maybe we get the amount of power, how much power injected with relation to the weather conditions, and this is so we can see the degradations. That's actually can be a good topics. Yeah. This is subject that we have access to the data. Okay, another question, which is Dr. Shiva. Okay, is protection in microgrid is integral part of the hierarchy control of the micro? Yes, it should be. Okay, it should be, because that's have to be linked, to be linked to each other. Yep. Another question: the difference between standalone, isolated, and autonomous microgrid. Yeah, it's very confusing. Very, very true. The terms. So in microgrid, if it is grid connected, it can operate on what you call grid connection and isolated. Okay. Standalone, the term standalone, usually we use it when there is no grid connections. Okay, so there is no grid, so there is no grid at all. Then we can see this is a standalone system. Okay, standalone system, so it's not. But if we have a grid connected, then we have two modes. We have either it is on a grid connected mode, or isolated. Means it just isolates from the grid, but we can be reconnected again. So I know it's a bit confusing, but just put in mind, okay? Microgrid, we have either grid connected or standalone. Standalone means there is no grid at all, okay? Right? So we have only one mode of operation. If it is what you call grid connected, we have grid connected mode and isolated mode operations. So sometimes autonomous also can be used, yeah, so it's sometimes it's a bit what you call confusing actually this, but just either is grid connected or is standalone. Okay, good. Any further questions?
I think,
Otherwise, I think we have time for exams now,
Yeah.
especially for people who are interested to pass the exam.